basic version I know of is Feynman's version, which essentially says particles are particles and they hop from place to place with a particular probability. And the probability that a particle that's at some place will be at some different place later is given by a very simple rule. It uses a quantity called the action, which is to do with the mass of the particle and the time and the distance. So you basically calculate these little quantities, which are to do with something called the action, and you add them up. So if I start with an electron in one corner of the room and I say what's the probability at some time later it'll be somewhere else, then at every point in the room you can assign a probability that it will be there at a later point with one simple rule, and that's it. Now this is called the path integral formulation of quantum mechanics. That underlies everything else. You can get the rest from that. So it's a simple rule. It says what's the probability a particle will move from A to B? That's it.
In modern physics, there's a theory that challenges our usual ideas about reality: quantum field theory. This theory delves deep into the basic fabric of the universe and reveals a world of tiny particles, fluctuating fields, and different scales of reality. Have you ever wondered what makes up reality? What's the scale of reality, and how does our consciousness shape it, from the smallest particles to the vast cosmic scale? Join us as we explore the mysteries of quantum field theory and its influence on how we see the universe. Quantum field theory is a theoretical framework that blends quantum mechanics with fields, offering a complete grasp of fundamental particles and how they interact. To get into QFT, we first need to explore the basics of quantum mechanics. Formulated in the early 20th century, quantum mechanics changed how we see the microscopic world. It brought in the idea of particles being inherently probabilistic, shaking up the traditional view of determinism. The wave-particle duality, shown in experiments like the double-slit one, revealed the built-in uncertainty at the quantum level. As physicists dealt with the implications of quantum mechanics, a big challenge came up: merging quantum principles with field descriptions. Classical field theories, such as electromagnetism, needed a quantum version to handle particle behavior at the quantum scale. This led to the creation of quantum field theory. Understanding the historical backdrop is key. Pioneering minds like Paul Dirac, Wolfgang Pauli, and Max Planck were crucial in shaping quantum theory. Dirac's quantum field equations, from the late 1920s, set the stage for QFT by expanding quantum mechanics to fields. These early efforts aimed to capture the complex interplay of particles and fields in a straightforward manner. Looking ahead, the need for a unified framework became clear. Quantum mechanics did well with single particles, but the challenge was extending this understanding to systems with multiple particles and their interactions. Quantum field theory emerged as the solution, offering a versatile approach to tackle these complexities. To dive into the basics of quantum field theory, let's grasp the fundamental ideas that make up this theoretical framework. Simply put, QFT blends quantum mechanics with fields to explain how particles behave and interact in a more advanced way. In QFT, the key idea is to see fields as the building blocks of nature. Unlike classical mechanics that focuses on particles, QFT shifts the focus to fields filling space. These fields, following quantum principles, show up as particles when energized a shift from classical physics. Getting into the nitty-gritty of QFT, we tackle the concept of quantizing fields. This means treating field values as operators with specific rules. This mathematical approach lets us create and remove particles within the field, giving us a dynamic way to understand particle interactions. Now, let's talk about the math behind QFT using Lagrangian formalism. This method helps physicists figure out the equations governing field motion, offering a unified way to describe how particles behave. Lagrangians capture the dynamics and interactions of fields, providing a straightforward and powerful tool for forming quantum field equations. As we dig into quantum field theory, a crucial aspect unfolds the dynamic interaction of quantum fields in action. Understanding how particles play out in this framework reveals the intricacies of nature at its most basic level. In QFT, particle interactions boil down to how quantum fields behave. These fields fill space, and when something disturbs them, we get observable particles. The language of particle interactions is neatly explained through Feynman diagrams, which visually represent the intricate dance happening within the quantum field. Feynman diagrams, despite sounding abstract, offer a practical way to understand the exchange of virtual particles during interactions. Each line and vertex in these diagrams stands for a mathematical amplitude, helping physicists calculate probabilities for different outcomes of particle interactions. By peeling back the layers of these diagrams, researchers get a sense of the underlying dynamics of quantum fields. A key concept in QFT is the idea of virtual particles. Unlike real particles, virtual particles exist briefly as intermediaries in interactions. They represent temporary deviations from the vacuum state of the quantum field. While these virtual particles may not directly show up in observations, their influence on particle interactions is crucial for understanding the quantum world. The electromagnetic force, explained by quantum electrodynamics or QED, provides a down-to-earth example of quantum fields in action. In QED, charged particles interact by swapping virtual photons. These virtual photons mediate the electromagnetic force, causing charged particles to attract or repel each other. The exchange process, shown through Feynman diagrams, illustrates the nuanced dynamics of virtual particles facilitating electromagnetic interactions. Moving beyond electromagnetism, QFT offers a unified framework for understanding the strong and weak nuclear forces. Quantum chromodynamics, or QCD, explains the strong force holding quarks within protons and neutrons, contributing to the stability of atomic nuclei. The weak force, responsible for processes like beta decay, is explained by the electroweak theory, showing the unity of electromagnetic and weak forces within the QFT framework. Observations from particle accelerators, like those at CERN, highlight the practical side of quantum fields in action. Experiments with high-energy particles reveal complex interaction patterns, confirming the predictions of QFT. Detecting particles and their decay products provides experimental evidence for fundamental forces mediated by quantum fields. Renormalization, a concept mentioned earlier, plays a crucial role in dealing with infinities in quantum field calculations. As particles interact, quantum fields lead to infinite quantities in certain calculations. Renormalization techniques offer a practical way to redefine parameters, ensuring predictions that make sense and align with experimental observations. This practical side of QFT emphasizes the connection between theoretical concepts and empirical validation. As we look into quantum field theory, its applications go beyond theory, proving useful in understanding the fundamental forces that shape the universe. Let's see how QFT is practically relevant in unraveling the complexities of particle interactions. One key application is quantum electrodynamics, where the electromagnetic force takes the spotlight. QED, designed to explain interactions among charged particles using photons, helps us understand phenomena from electron behavior in atoms to electromagnetic field dynamics. The precision of QED predictions, confirmed through experiments, highlights its practical usefulness. Moving to quantum chromodynamics, it helps us understand the strong nuclear force binding quarks within protons and neutrons. Successfully applied to describe hadron structures like mesons and baryons, QCD sheds light on subatomic particle intricacies. The colorful world of quarks and gluons, as explained by QCD, contributes to our grasp of quantum fields. Another facet, the electroweak theory, unifies electromagnetic and weak nuclear forces, offering a coherent view of particle interactions. Experimental validations, like discovering W and Z bosons, support the electroweak theory's success in capturing these forces' intricacies. The standard model of particle physics, integrating QED, QCD, and electroweak theory, serves as a comprehensive framework for understanding elementary particles and their interactions from quarks and leptons to gauge bosons. Practically, QFT applies to studying high-energy phenomena in astrophysics and cosmology, helping understand particle interactions in extreme conditions, like the early universe or near black holes. Exploring cosmic mysteries, from neutron star dynamics to dark matter behavior, relies on QFT principles. In condensed matter physics, QFT finds use in describing collective phenomena in materials. Concepts like quasi-particles and phase transitions benefit from tools borrowed from quantum field theory, showcasing its versatility beyond particle physics. Beyond theory, QFT contributes practically to technological domains, influencing advanced materials, quantum computing, and novel technologies. The fusion of theoretical insights with practical innovation demonstrates QFT's broader impact on shaping the technological landscape. As we explore quantum field theory, it's important to consider the current challenges researchers face and potential directions for the future of this complex theoretical framework. While QFT provides insights into the microscopic world, it has its limitations and unanswered questions. A significant challenge is aligning QFT with general relativity to create a unified theory of quantum gravity. General relativity, dealing with gravity on a cosmological scale, and QFT, governing the microscopic realm, don't quite match up. Integrating these two aspects of modern physics into a coherent framework has been a long-standing challenge. Another area of interest is understanding dark matter and dark energy, which make up a large part of the universe's mass-energy content. Despite QFT's success in describing known particles and forces, it hasn't fully accounted for the properties and interactions of these mysterious components. Unraveling the nature of dark matter and dark energy is crucial for a more comprehensive understanding of the universe. Quantum entanglement, often referred to as spooky action at a distance, presents theoretical and philosophical challenges. While QFT provides a framework for understanding entanglement, the non-local correlations between particles challenge classical intuition. Exploring entanglement's subtleties and its applications, such as quantum communication and computing, remains an active area of research. QFT faces mathematical challenges, particularly in dealing with complexities in certain scenarios. Some calculations lead to infinities that require renormalization. While this technique is effective, questions arise about the nature of these infinities and the robustness of the theoretical framework. Researchers aim to find more elegant and comprehensive mathematical approaches to address these challenges. The search for new physics beyond the standard model is another focus. While the standard model aligns with experimental data, it falls short in explaining phenomena like neutrino masses, dark matter nature, and matter-antimatter asymmetry. Exploring these mysteries requires both theoretical innovation and experimental exploration. Thanks for joining us. If you liked it, hit subscribe, and we'll keep sharing cool stuff. See you in the next video.